Today we will be discussing this example here. So the first part is exactly the same as we discussed in the previous lecture, and we solved the first part using graphical procedure. Today we will be discussing the analytical procedure. So as you can see in this figure here, that a shaft located in two bearings at D and E. So these D and E are two bearings, carries three pulleys at A, B, and C, and we have three pulleys which are attached at location A, location B, and location C. And each pulley carries an out of balance mass as indicated. So these are the out of balance mass in this case. So the out of balance mass at location A is shown here. The out of balance mass at location B is at angle of 60 to the vertical. And similarly, the out of balance mass at location C is at an angle of 210 to the vertical. Okay, so you need to determine the magnitude of the out of balance forces at bearing D and E when the shaft rotate at 1000 RPM. So what you are given here is that omega is given, which is 1000 RPM. So this is given, and what you need to calculate, RE, which is the reaction force at location E, and you also need to calculate the reaction force at position D here. Okay, so we need to calculate these, but now we will try to solve this problem analytically. Uh, the procedure is the same, so we'll be using the same equations, and we know that for dynamic balancing, we have these three conditions: that summation of all the moments at D equals 0, summation of all the moments at E equals 0, and summation of all the forces equals 0. So we have these three conditions here. So out of these three, we will use one up from 1 and 2. So we will use either 1 or 2, and then we will use 3. Okay, so now if we take the moment from D as we did in the previous case, so if we just use this condition here, summation of all the moments at D equals 0, and if we take this direction is positive here. So as you know that the if we have a force here, another force here, so in this case, if you consider these two forces, so this positive force is creating the clockwise moment, and this positive force is creating a counterclockwise moment. So this means that this positive force will create a negative moment, and this positive force will create a positive moment. So it's also important to make sure that you know the direction of the moment here. So for the first case, for the first force, which is this force here, uh, we will use this condition here, the summation of all the moments at D equals 0. So we will take the moments from location D here. So first, you are also given these MARA, MBRB, and MCRC. So from these, you can also calculate the actual forces. If you multiply this with the omega, you can calculate the actual forces. So the first force, which is FA, is equal to MA RA omega square. And you can calculate this, which will be 329 Newton. Omega is given, which is 1000. So if you multiply with 1000 square, and you will need to convert this into radian per second. So if we just do it properly, so it will be 0.03 into 1000 into 2 pi divided by 60 into square, and this will give you 329 Newton. Similarly, F in the B direction will be equal to MARA MBRB omega square, which will be 0.04 times the same 1000 into 2 pi divided by 60 square, and this should provide you with the 438.6 Newton. Similarly, you can calculate FC, which is going to be MB MCRC omega square, and MCRC is 0.02. So if you multiply this with the 1000 RPM, so convert this into radian per second, and this will be 219.3 Newton. So we have these now the actual forces, not just MARA or MBRB or MCRC, but now we have the actual centrifugal forces, which is given in Newton. So now from these forces, you can calculate the moments. So as we know that FA is positive here, which is 329, and we are taking the counterclockwise moment is positive. So we know that this positive force will create a clockwise moment, which will be a negative. And again, we are taking the direction of the moments in the direction of the forces. So similar to the previous case, we know that the moments in this case will be the FA into DA will be in this direction here, and DA is actually this distance here. So this is our DA here, which in this case is 200 millimeter or 0.2 meter. So if you calculate this FADA, this will be 329 into 0.2, and this is negative because is a clockwise Newton meter here. So this is our moment that we have in the vertical direction here. So now the way the analytical procedure works is that we will try to find out the x and y component of this moment here. So the x component in this case, because it's just a vertical vector, so its x component is 0 and y component is minus 65.8 here. So this is how you will do it. Now for the MBRB or the FB, so we know that because it's in the upward direction, so obviously this will create a force, a moment which will be counterclockwise, which will be positive. So you can say that it should be in the direction of the force here, which is in this direction here. So this is our F, B, and DB. So FB, as you can see, is acting here, and the distance from here to here is 600. But we are taking moments from D, so you will just multiply with this distance here from here to here, which is 0.4. And FB is 438.6 times 0.4. So this will be 175.5 Newton meter. And again, we can split this into two components. So this angle is given, which is 60 degree. This means that the angle with the horizontal is 30 degree here. So now we can split this vector into two direction, x and y. So as you can see that the x component will be equal to 175.5 into cos of 30, which will be equal to 152 Newton meter, and the y component will be 175.5 sine of 30, which will be equal to 87.7 Newton meter. And these are also should be in the Newton meter. Okay, so we have this x and y component of this. Now, as you can see, this MC, so this MC again is acting in this direction here, and it's toward this side here. So the direction of the force will be again in the direction of the moment will be in the direction of the force. So we can again know that the angle of this mass is 210 with the vertical. So if you draw this, so this means that this angle is 210, or you can say that this angle with the, you calculate this, so this angle will be 60 degree. You see a 60-degree angle here, a 60-degree angle, and this is our moment, which is equal to FC time DC. So DC will be the distance from D to C, and which will be 1500 minus 200, so which is 1.3. And FC that you have here, so 219.3, multiply with the 1.3. So this will be 285.1 Newton meter. So you calculate this value here. So now, similar to the previous two cases, you can split this into x and y component. So the x component of this will be equal to 285.1 into cos of 60 degree. But as you can see in this case here, that the x and y component of this will be in this direction here, and the y component is in this direction here. So obviously it's in this direction, so it's negative, and the y component is also negative. Now for this case, the x component was in this direction and the y component was in this direction, so both were positive, and it is in the opposite direction to this one, so therefore we will take these as negative. So this will be minus because it's to the left, so therefore it's negative. So minus 42.6 Newton meter, and similarly the y component is going to be 285.1 sine of 60 degree, and this will be minus 2 for 6.9 Newton meter. Okay, so we managed to calculate all the moments relative to position D. and we also managed to calculate the x and y component of each moment. So each moment was due to these force A, force B, and the force at C. Okay, so in the next we will try to apply the this condition of yeah. So now we will apply the condition that summation of all the moments at D equals 0, and obviously we are taking this direction is is a positive. So as you can see that if you look at this figure here, so now we can split this into two components, x and y. So if you take the x, if you apply these to the x direction, so this means that the moments of all the forces which can be split into x direction. So what do you have? You will have the similarly one force will be acting at D, the reaction force at at E. So which will be R E x, and the distance will be from here to here, which is 1200 minus 200. So which will be just 1. And for other part, we have all the x component and y component. So for the FADA, we have the x component which is 0. For FB DB, we have the x component which is 152. So positive 152. And for the FCDC, we have the x component which is negative, so minus 142.6. And if you put this equal to 0, so from this equation you can calculate this will provide you with the REX. This means that the reaction at E, but only the x component, so which is minus 9.4 Newton. Similarly, you can take the moments in the y direction. So the moments in the y direction, obviously you will start with the R E Y, so which is the component of the reaction in the y direction. And again, the distance here is 1, from here to here is 1. And now you have the component of this FADA, which is minus 65.8. And now you have the this component here, which is in the y direction, so 87.7 but positive. And finally, you have this component here, which is minus 246.9. And this should be equal to 0. So this will provide you with REY. And if you calculate from this equation, the only unknown is REY, so you can calculate this. And this should be equal to 225 Newton. Okay, so you managed to calculate REX and REY. So from this now you can calculate RE, which is simple REX square plus REY square, because this is the x and y component. So you can calculate this value, which is 9.4 square plus 225 square under the root, and this will be 225.2 Newton. Now you can draw this this vector. So for example, if you draw the coordinate system here, This is our x, this is our y. So as you can see, the rex is negative. So this means that the direction of rex is in this direction here. So minus 9.4, and then the direction of the rey is positive. So then and it is 225. So this means that the final vector was in this direction here. So this is our rex. This is our re. So the value of the re, and you can calculate this this angle here. You can calculate this angle here. So angle theta will be equal to tangent inverse 225 divided by 9.4, and this will be 87.6 degree. But as you can see in this figure, we are taking all the angles from this vertical in this direction here. So as you can see in this case, the angles will be, if you take this angle here. So if you want to calculate this angle here, so this will be 90, 90, 90, which is 270 plus 87. So then the angle, if you say with respect to y, so this will be 270 plus 87.6, so which will be 357, which is the same angle as we calculate in the previous example. And also the RE is exactly the same as we did in the previous example. So again, we can use this procedure to calculate the reaction forces, and also we can calculate uh, the out of balance mass using this procedure. Okay, so we managed to calculate the RE. Now in the second part, we need to calculate now the reaction force at D. So the second thing that we need to calculate is RD. So for the RD, we will be using the summation of all the forces uh, equal to 0. Now, as you know that we have all these forces. So we have FA, FB, FC, and similarly we also have the this RE here. So we can just do it very easily. So as you can see from so if you just say the FA, so FA is in the vertical direction here. So FA is 329, uh, and we can calculate its x component, which is going to be uh, because this FA is in the vertical direction, so it x component will be 0, and its y component will be equal to 329. Similarly for the FB, which is 438.6, and the direction of this force is obviously in the same direction as this one. So you can calculate its x value. So x value will be equal to uh, 438.6 cos of 30, so which will be 379.9, and the y component, which will be equal to 438.6 into sine 90, sine 30, so which will be 219.3. And for FC, which is 219.3, and which is going to be along this direction here, which is along this direction here. So in this case, it will have two components, which one will be in this direction, one will be in this direction. So 219 cos 60 will be in the x direction, and 219 sine 60 will be in the y direction, but both will be negative here. So if you calculate its x component, which will be minus 109.7, and its y component will be equal to minus 189.9 here, and all these are obviously in newtons. And we are also given the RE. So RE, which we have, is the reaction at location E, which is 225.2, and it have x component, which was minus 9.4, and its y component was plus 225 Newton. Okay, so now if we have this condition, so now we can apply this forces in the x direction now, and then we can do in the y direction. So in the x direction, now we will have rdx, which is the reaction force at location D, which is this location here, and then we can add all these components together here. So plus 0, which is fax, and then fbx, which is 379.9, and which is positive, and then plus fcx, which is negative, so minus 109.7, and then plus rex, so which is minus 9.4, and this should be equal to should be equal to 0 here. So from here we can calculate rdx, which is going to be minus 260.8 Newton. And now we can apply all the forces in the y direction. So it will be rdy, and then you have 329, which is the fay. Then you have the fby, which is plus 219.3, and then you have this minus 189.9, and then you have plus 225, which is all the forces in the y direction, and this will be equal to 0. So from here then you will be able to calculate r dy, so which will be equal to minus 583.4 Newton. So now we have rdx and rdy, so we can even draw the vector here. So if you draw the x and y coordinates here, so you know that you can this rdx is negative, so this means that you have to go in the negative direction here. So this is 260.8 in this direction. And then again, you need to go in the negative y direction. So which is 583.4. And then the final vector will be this here. So this will be our RD, and which you can calculate from here. So RD will be RDX square plus RDY square. So this should provide you with the value, which is 639. So this means that this is 639 Newton, and you can calculate this angle here. So you can call this theta d, which is tangent inverse uh, tangent inverse 583.4 divided by 260.8. So this will provide you with the value of this theta d, which is 65.9 degrees. But now if you want to calculate the angle with respect to this position here, so if you want to calculate this angle here, so this angle which is the which you can say alpha d. So alpha d is the required angle here. So which you can say in this case is this 90 and then 90 and then 90. So 270 minus theta d, which is going to be 270 minus 65.9 degrees, which is 204.1. So by using this procedure, you can calculate uh, the reaction force at location D, and also its angle. Similarly here, you can calculate the reaction force at E and its angle.